Okay, hi everyone. Good morning. It's 9:20 now, and this is Sarah. I'm the TA for this course. So I'm going to be leading the course today. I'm sure Mark told you this last week. And so we're just going to continue where you guys left off last week, and we'll move on to set operations. So we'll review Cartesian products, which is very I think you guys left off, and then we'll move on to set operations. I do want to say one thing that I can't see the chat option or the chat box while I'm going to be writing. So if you guys do have any questions or you want some clarification, so just unmute yourselves and just say something, because I'm not going to be able to see if you raise your hand. So yeah. Does anybody have any questions about anything? If not, then I'll get started. I think you can all see my screen now. Okay. So first, we're going to review the definition of a Cartesian product. So I'm going to write it for two sets. So let A and B be sets. Then we define the Cartesian product, and Cartesian product of A and B, which we denote by A cross B, is the set of all ordered pairs of the form A comma B, where A is in A and B is in B. So we can also write this in set notation as A comma B. A is in A and B is in B. Okay, so we can also do this for more sets than just two. Like you can also take the Cartesian product of A cross B cross C. That's also okay. We just extend the definition so that it works for A cross B cross C. So we'll do an example to review. So this is going to be just a simple example. So suppose that A is equal to 1 comma 2. Then we want to find A cross A. So we can also write this as A squared. And so to find this is going to be the set of all here, as you can see, the set of all A comma B, such that A is in A and B is in B. But here we don't have a B, so we just have A. So this would be 1 comma 1, 1 comma 2, 2 comma 1, and 2 comma 2, and these are all the possible combinations that you could have. So that's just a simple example, but we can do another example. Does anybody have any questions so far? Is everything okay? I'm going to take the silence as everything's okay. Okay, so the next example, we'll try to work with the set of real numbers R. And so if you do, let's say R cross R positive. So R positive, what I mean is the set of all X in R such that X is greater than 0. So if we were to sketch this Cartesian product out on the XY plane, then this would look like, I'm going to draw it. So this is the XY plane. So first we have, so this one tells us all of our X's, and this one you can think of as telling us what our Y's are. So the first one says that we can have all the X's, and the second one is saying that we can only have positive Y's. So if I were to shade that in, that would look like this part, and not including the x-axis, because that's when y is equal to 0, and we want r plus, so we don't want 0. So that's another example of a Cartesian product. Okay, does anybody have any questions about this example? Okay, if not, then now we're going to talk about relations. So I'm not sure if you guys talked about relations before or not, but so I'm going to, well, maybe you guys did. I don't know, can someone let me know if you guys talked about relations before or not?
We haven't.
Okay, okay, all right. So I guess that you do know that Cartesian products are just relations on sets. Okay, so I guess then we can move on to set operations. So this is, I think this is the next section in the textbook. So we're going to start with unions. And so I'm going to define what a union is, and we'll do some examples. Okay, so I'll just write set operation.
I think you might have
Yes.
misread it. I said we have not talked about relations. Sorry.
Oh, okay,
Yeah,
okay. I'm so sorry. Yeah, I
you're good.
definitely misheard. I
Okay.
thought you said we have. Okay. Um, all right. So, all right. So let's say that. So I'm going to define relations. Okay. So I'm going to say definition. So let's say that we have the Cartesian product A cross B. So a subset of this Cartesian product. So a subset of this Cartesian product is called a relation from the set A. Maybe I should underline the words that I'm defining, to the set B. So the set A to the set B, so that's just the first one to the second one. So we know that Cartesian products are, well, the Cartesian product of A cross B, the elements of this Cartesian product have the form of A comma B, right? So relations are a subset of a Cartesian product, so they're also going to have this form. And so to see this better, maybe we can do an example. For example, let's take this. Let's say A is the set A comma B comma C, and let's say that B is the set 0 comma 1 comma 2 comma 3. Then we could write out the whole Cartesian product, but I don't want to do that because it's there's going to be quite a few elements to write out. So I'm just going to write a relation on a relation from the set from the set A to the set B. Sorry. So usually we denote relations by R, by the way. So maybe I should write that in the definition. A subset of the Cartesian is called a relation denoted like by capital R. So that's usually how we denote relations. So, okay, so an example, you can define many different types of relations from the set A to the set B. So we're just going to do one example. An example of a relation is, let's say R is equal to A comma 0, A comma 1, and then I'll just skip B and I'll just do like C comma 2, for example. So they're like, they have the elements have the same form as the elements of the Cartesian product, but they don't have to be every single element that's in the Cartesian product. Basically, it's just a subset, so it can just be some of them. So here I just took 3 instead of taking all of them. So that's an example of a relation from this set A to the set B. and this definition continued of the previous one. If you have a relation from the set A to itself, then we call that relation as relation on A. So, okay. If we have a relation R from, then we call it a relation on A. So that's just terminology. I guess I'll underline this, a relation on A, and not underline those. Okay, so in the future, you guys will be discussing functions from a set to another set, and I'm sure everyone has seen a function before, but relations are basically generalizations of functions. So for functions, when we have a set A, when we take a function from a set A to a set B, we usually have like this rule. Well, that's the definition of a function, the rule that to every element of A, we need to assign some element from B. So relations are basically generalizations of that. But instead of having, so like, for example, if I were to draw this relation now, visual, like if this is A, so I'm just going to draw like points to denote the elements, and this is, let's say, B, 0, 1, 2, 3. So this relation R, what it does is that it takes A to 0, but it also takes A to 1, as the second one says, and then it takes C to 2. So for a function, we would need that A, B, and C are all taken to some element in B, and they're not taken to multiple elements. But for relations, you're not, like, you don't have such strict conditions. So they're basically like a looser form of a function. But yeah, but the formal definition is that it's a subset of the Cartesian product of A cross B. So yeah, so that's what I want to say about relations. And we can do another example that's not maybe like just a few elements. So okay, so consider or maybe well, I want to do an example that's not just like, I guess, made up, but okay, so consider the relation, oops. Okay, consider the relation less than or equal to on 0, 1, 2. So what are the elements of this relation? So let me explain what I mean by relation on 0, 1, 2. What are the elements of this relation? So the less than or equal to relation on 0, 1, 2. So what I mean is that, oh, by the way, this is another way to write things. Maybe I should have said this before, but if you have, so this is like a side thing. Before we continue with the example, A comma B in the relation R, you can also write as A, R, B. So, and you would read this as A is related to B under R. And this is just another way of writing. And the reason why I like this notation and why I mentioned it for this example is because when we have the relation of less than or equal to, we can use that instead of R, and it's kind of easier to see what's going on. Okay, so we have this relation less than or equal to on 0, 1, 2. So what I mean is that I want to know which elements are in this relation. So basically, like which A comma B are in this relation so that A is less than or equal to B. So they have to satisfy this condition of being less than or equal, of A being less than or equal to B, and that would mean that they're in the relation. So that's kind of what I mean by consider the relation less than or equal to on 0, 1, 2. So one element, for example, would be 0, 0, because 0 is less than or equal to 0. And another one would be 0, 1, because 0 is less than or equal to 1. So can anyone give me the other elements of this relation?
Zero, 2, and 1, 2.
Yeah, 0, 2, that's good, and 1, 2. And there are two more.
And then 1, 1, and 2, 2.
Yeah, exactly. 1, 1, and 2, 2. So these are all the elements of the less than or equal to relation on 0, 1, 2. Does this make sense, or is it confusing? I don't know. Is it okay?
I think so.
I heard someone say, so it's like, okay. So what if you change this relation from less than or equal to just less than? Then which elements would be in the relation? So we wouldn't have 0, 0 because, I'm sorry, what?
Would it be just the first four?
The first four?
Yes.
Well, we wouldn't have 0, 0 because 0 is not less than 0, right? So not the first one, but yes, the second one, the third one, the fourth one, and yeah, that's it. So we wouldn't have the 0, 0, 1, 1, and 2, 2. But yeah, so right, so that would be the less than relation on 0, 1, 2. So maybe this, I just want to relate it back to the example. The definition. So the definition says that a relation is a subset of the Cartesian product A cross B. But in this case, we're taking a relation on 0, 1, 2. So we just have it on one set. So it's a subset of. So this relation should be a subset of 0, 1, 2 cross itself. Because it says on, so that's when you have just the set cross with itself. So as you can see that all the elements of this relation are, pairs of elements from the set 2. So it is a subset of the Cartesian product of the set with itself. It's just that, when you encounter like questions, it might not always be in the form of the definition. Usually they do write it like this, like consider the relation blah 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 on this set. So that's why I wanted to introduce this example instead of the previous one with just A and B, in which I just wrote some element from the Cartesian product. Okay. I didn't want to write so messily, but yeah, if you guys have trouble reading my handwriting, then let me know. I know it's not the best, so I'll try to write better from now on. Okay, so I'm not going to talk about a special form of relations which are called equivalence relations. Maybe Mark will cover that later. I wasn't sure if I should cover that or not because it wasn't part of the textbook that Mark asked me to cover, so I'm not going to cover it, but maybe he will come back to relations, and these special relations are called equivalence relations, and they have like some properties that they need to fulfill to qualify as an equivalence relation. So maybe you guys will talk about that later, but that's all in relations for now. And so we'll move on to set operations. So set operations. So the first one, like I said before, we're going to start with unions. I'm not sure how many of you have taken any set theory before. So we're going to start from the definition of a union. So, so the definition. So suppose you have two sets, let A and B. Also, if I'm rushing, then please ask me to slow down. I'm not an instructor, so you don't need to be like super careful with me. So let A and B be two sets. Then the union of the sets. Oh, all right. I said I'll write later. Okay. The union of the sets A and B, denoted by A, U, B. So this is the notation for unions. It's just a U between the two sets. Is the set that contains those elements that are either in A or in B, or in both. I don't know if this is necessary to say because or is supposed to include both, but I'll just write this so that nobody forgets this case. So a union of A and B is basically you take all the elements of A and you take all the elements of B and you put them together in one bigger set. So if I were to draw a picture of A, like let's say this set is A and like this is B. So their union, I'm going to shade it in, their union would be all of this. So it would be all the elements of A and all the elements of B. So the blue would be A union B. Okay, is that okay? Okay, all right. So I can write this in set notation. So A union B is equal to the set of all X such that X is in A or X is in B. So this is the definition of a union. Okay, so again, we can extend this definition. So we can extend to, for example, three sets A, B, C. So that would be written like A union B union C. So that's so this would be defined. Do you guys know, like if you put two dots and then equal, it's supposed to be for definition. I don't know, I'm just clarifying. So that would be defined. It's nothing more, it's just saying that like, this is the definition. So this is the definition of A union B union C. So X is in A, or X is in B, or X is in C. So now you would take all the elements of A and all the elements of B and all the elements of C, and that would be A union B union C. Okay, so I think this is pretty okay, I hope. So we can do examples. So let's start with easy examples. So if we do 1, 2, 3, and we do union with 4, 5, 6. So what do you think this union would be?
It would
So we have to take, oh, I'm sorry, someone
yeah, I was just gonna say
to
it
answer.
would be the set 1, 2, 3,
Yeah.
4, 5, 6.
Yeah, exactly. So that would be the set. Great. So that's the union of these two sets. And what if I did 1, 2, 3, union 1, 2, 3? Then what would it be?
1, 2, 3.
Yeah, exactly. So this is basically saying that, well, I mean, you have to do like an actual proof. An example is not sufficient. Also, that's something that I want to say about the homework, since I grade your homeworks, that just if you have a proof, an example is not sufficient as a proof, but it's a good place to start, I think. So if you have two sets that are, I mean, if you have A union A, then the union is that union is always equal to A because you're not adding anything more into the set. So it's just equal to itself. Okay, so let's do a harder example maybe. So let's say that we have the natural numbers. Oh, I have a question. Do you include 0 in the natural numbers in this class, or do you start from 1? Because some classes include 0, but some classes don't include 0.
We usually include 0, but we say positive
Oh, okay.
integers if it's not including 0.
Oh, okay. Yeah, that's that. I like that way. Okay, so this is I'm just writing this down so that people know what I'm referring to. Okay, so that's all of these numbers, and then we have z. So that's the integers, right? So that's 0 plus or minus 1 plus or minus 2, and so on and so forth. So if we take the union of the natural numbers and the integers, what do you think the union would be in this case?
The integers again?
Yeah, exactly. Because so it's the integers because the natural numbers are a subset of the integers. So you're not really adding anything new to the union. So it's just the integers. So this also is something that is always true, that if you take a subset union with the superset, so by superset, I just mean the set containing the other set. And it's kind of redundant, I guess, subset and superset. Okay, but like if you take a smaller set and you union it with the bigger set that contains it, so the union is always going to be equal to the superset, because like I said, you're not really adding anything new to the union by unioning it with the subset. Okay, so another example, let's say that we do the singleton, which just means a set consisting of one element, if you haven't heard that before. So that's just the set containing one, union the empty set. So what do you think this would be? Does anybody know? So the empty set is not adding anything new to this union. So, and if you recall, I don't know if you've done this before, but the empty set is a subset of every set. Have you guys did that before, or is that news?
Yeah, we've been over that.
Yeah, so we're taking one union, something that's a subset of that set. So that would just be 1, because the empty set has no elements, so it's not really adding anything to the union because it doesn't have anything to add. So yeah, so this is also a side thing, which is kind of a consequence of the thing above, but any set union with the empty set is equal to that set. I'm sorry I'm writing it like this, but I hope you can write it better in your notes, but yeah. Okay, so, all right, so let's do another example before we move on to intersections. And this example is going to be a little bit more challenging, I think, because we're going to take unions of more than 2 sets. So like I said, we can extend the definition to 3 sets, but it's not just limited to 3 sets or 4 sets or 5 sets. In fact, you can take a union of an infinite amount of sets. That's okay too. So that's what we're going to do now. Maybe I shouldn't jump from 2 to an infinite amount, but that's what I have in my lesson plan, so I'm just going to follow it. But if you guys have any questions, then please ask me. So, so this is, so first I'm going to start with the notation that I have above, and then I'll write the usual notation that this is written in. Okay, so let's say that we have 1 comma, or 1 over 1, sorry, 1 over 1 to infinity. So this is the interval. I'm writing 1 over 1 instead of 1 because next I'm going to do 1 over 2, so I just want it to be consistent. So this is the interval from 1 to infinity. So let's say I take the union of that with 1/2 comma infinity, and then I take the union of that with 1/3 comma infinity, and so on and so forth. So usually like this, writing it like this is kind of, it takes up a lot of space. So I guess you can write it like this, that let's say that n goes from 1, or a better way to do it is, let's say that n is in, you guys said positive integers, right? So I'm going to write z plus, so that's the positive integers. And we have 1 over n comma infinity. So I'm just rewriting it. So this is just a way to write it. So you just write like this big U, and then you write whatever next to it that you're taking the union over. So we're taking union over all of these intervals. So if I were to draw this out, it would look like this. So I'm drawing it out on the real number line, because we're taking intervals from the real numbers. So let's do 0 here, and 1 and 2 and -1 just for the sake of it. Okay, so I'm going to, I guess, change colors. So the first one is this, and I'll color it in. So it goes on to infinity, so there's no end. And then the second one is the set. And then the third one would be that set, and so on and so forth. Okay, so we're taking oh no, that's not what I meant. I'm so sorry. If anyone noticed, I made like a huge mistake. I didn't mean to do that, because I was like, wait, that's not what I was going for at all. Okay, I'm sorry, my drawing was off, like way off. Okay, so 0, 1. I was thinking like I'm taking the union of 1 to infinity and 2 to infinity, which is not what I meant to do. Okay. Wait, I think I meant, okay, that's fine, I guess. Yeah, okay. All right, so, oh, I didn't mean to draw it here. I'm sorry, this is taking some time. But I want to draw it out so that it's easy to visualize. Okay, so the first one is like before, but the next one is not from 2 to infinity, it's from 1/2, which is what I meant to do, but I didn't. Okay. Okay. And then the next one would be from 1/3, which is like somewhere here. Okay. Now I think it's okay. All right, so we're taking the unions of all of these intervals, and we want to know what the union should be. So and this goes on here. So like it keeps, you have 1/4 to infinity, 1/5 to infinity. So I just don't want to draw all of it, and I also can't. It's impossible. But okay, so does anybody have any idea of what this union should look like? Like looking at the picture, what do you think it should look like as we keep adding more of these intervals to this union? So as n is going to infinity, what do you think this union should be going to?
Is it from 0 to infinity, not including 0?
Yeah, exactly. That's exactly right. So that's what the union is of this. And so I'm just copying it so I can write equal to. So I just want to say one thing, like that it's interesting that here we had closed intervals, but here we have or half closed intervals, and here we have an open interval. And that sort of thing can happen with unions when you go, or when you take unions, an infinite amount of unions. So so these kind of things can happen with unions, and you'll see more of this maybe in like future courses, that we took a union of closed intervals or half closed intervals, and we ended up with an open interval. So yeah, so these sort of things can happen. But yeah, so is this example okay with everyone? So the reason why it's 0 is because we take the limit as n goes to infinity of 1 over n, and that's equal to 0. And so that's why we have 0 here. And the reason why it's open is because it never actually reaches 0. So none of the intervals actually contain 0. So their union also can't contain 0. So that's why it's an open interval. So if that's clear, if anybody has any questions, I'll wait for a few seconds before moving on to intersections. Okay, so next we'll do intersections. Okay, so next we'll define what an intersection is first. So let A and B be sets. The intersection of the sets A and, oh, maybe I shouldn't write and like that. But if you ever see this, I mean and. It's just the way that I write my notes. Oh, here. Okay, so that stands for and, just in case anybody's confused. So the intersection of the sets A and B, our underline intersection, denoted by A. So here we just have like an upside down U. So that's for intersections. So denoted by A intersection B is the set containing those elements that are in both A and B. So unions, we had or, and intersections, we have and. So basically, intersections are the elements that both the sets have in common. So if I were to write this out in set notation, I would do A intersection B is equal to X, or defined as the set of all X such that X is in A and X is in B. So X needs to be in both of them to be in their intersection. And this definition too, we can extend to 3 sets or 4 sets or an infinite amount of sets. So it's not just limited to 2 sets. So it's the same as unions, that you can take intersections over any amount of sets that you'd like. So any collection of sets that you have. Okay, so let's do examples. We'll kind of do like similar ones to the ones that we did for unions. So first one, 1, 2, 3. Intersection with, or intersected with 3, 5, 6. I don't know what the word was, but anyway, so the intersection of 1, 2, 3, and 3, 5, 6. So what would this be?
The set containing 3.
Yeah, exactly, because that's the only element that both these sets have in common, so it's a set containing 3. And then let's say that we do 1, 2, 3, intersected with 2, 3, 1. So what would this set be?
Does the order matter? Would it be 1, 2, 3?
Yeah, it would be 1, 2, 3. And the reason why I did this is exactly because the order doesn't matter. So this is like a thing for sets in general anyway, that if you have a set with like elements A, B, and C, then if you have another set that also has elements A, B, and C, then those sets are equal, because it doesn't really matter how you arrange A, B, and C. You could even I don't know, write them on top of each other. As long as you say that you have these elements A, B, and C that make up this set, any other set that's also made up with A, B, and C would be equal to that set. So yeah, the order doesn't matter when you write sets. It's just like sometimes, I mean, I don't know, 1, 2, 3 is a better way to write it. I guess that's arguable, but yeah, I just wanted to shuffle it to make it clear that the order doesn't matter. So this would be 1, 2, 3. And oh, I don't know why I keep writing parentheses, but okay. So it's true in general that if you do A intersected with A, that's equal to A. And that makes sense because the elements that A has in common with A are all the elements that are in A, so that should be equal to A. So let's say that we do natural numbers intersected with the integers again. So what do you think this should be?
The natural numbers.
Maybe I'll write this out. Oh yeah, I was gonna write it out just so that it's clear, but I guess I won't. Okay, so this would be the natural numbers, and that's because the integers contain all the natural numbers, so it's equal to, their intersection is equal to their natural numbers, but the natural numbers don't contain any of the negative integers, so we can't include any of the negative integers. And this is also a fact that's true in general, that if you have a subset and you intersect it with its superset, so the set containing it, that should be equal to the subset. Oh, I wanted to draw a diagram, so I'll do that. I forgot. So if we have A and we have B, like before, the intersection would be these elements in here. So like this is A, this is B. This would be the elements that A and B have in common, and so that's their intersection. So like if I were to draw this picture out, like you have a superset and you have some other set living inside. So the intersection is the subset. This is the superset, this is the subset. Okay, so again, this same or similar example to before. If we do the set containing 1 intersected with the empty set, what do you think this set would look like?
Would it be the empty set?
Exactly, because the empty set doesn't have any elements, so this set here, the set 1, or the set containing 1, can't share any elements with the empty set, so it's the empty set. And this is also a fact that's true in general, that any set intersected with the empty set is equal to the empty set. And that's also kind of like a consequence of here, because the empty set is a subset of every set. So like I said, if you have a subset and a superset and you intersect them, their intersection is equal to the subset. Okay, now let's do a similar example to like the one we did before, but it's going to look a little bit different. So let's say that we took the intersections of -1/1, comma 1/1, and then we intersect it with -1/2, comma 1/2. So I mean the intervals, and then the interval from -1/3 to 1/3, and so on and so forth. So if I were to write this out concisely, I would say n is in z plus, and we're doing -1/n, comma 1/n, these intervals. So I'm taking this intersection. So you just write the intersection symbol really big, and then you write on the bottom what you're taking what the index is. So that I'm taking all the n in z plus, and then on the side you write down the things that you're intersecting. Okay, that's all very informal, but I hope it gets the point across. Okay, so if I were to draw this one out, and I hope I don't mess up this one, I'll try not to. So I have 0 here, and then I have -1, 1, -1/2, and 1/2. negative 1/3 and 1/3. That's all I'll draw, but I'll just write dot, dot, dot. Okay, so I do, oh, I had open interval. So this is the first one, the first set inner intersection. Then the second one is from negative 1/2 to 1/2. And then the third one is from negative 1/3 to 1/3. So this one, okay. And we keep going on. So from negative 1/4 to 1/4, that interval. So what do you think this intersection should look like?
The empty set.
I guess that's a good guess, but it's not actually the empty set because there is one element that all of these intervals have in common, and you can kind of see it in the drawing.
Would it be 0, 0, but not including 0?
So, what do you mean 0, 0? 0, 0? Like, do you just mean 0? I'm thinking like 0, 0. Oh, I see. Oh, you mean the interval. Oh, okay.
The interval,
Okay.
yeah.
Yeah. Okay. So actually, it is including 0 because so actually the interval would be 0, 0, or I can just write 0. And the reason is because all of these intervals contain 0, and the intersection is basically all the elements that are contained in all of the sets. So -1, the interval from -1 to 1 definitely contains 0, and so does the interval from -1/2 to 1/2. And if you keep going on, then if you take any one, like whatever interval you want, if you take any -1 over n to n, this interval would contain 0, right? Because n is some positive integer, so it never really reaches infinity. So that's why it never really not contains 0. So they all do contain 0 because you never actually get to infinity, even though the limit is taken as n goes to infinity. So all of these do contain the element 0. So that's why 0 is included. Is that okay?
Yeah, that
Yeah,
makes sense.
okay.
I'm just wondering, it doesn't matter that n is in the denominator and can't be equal to 0. That was kind of my rationale for saying that it wouldn't include 0, but that's not.
Yeah, so I wrote positive integers here because I didn't want to do the -1 over 0 to 1 over 0.
Oh,
So
okay.
yeah. So we're starting from 1, and then we go to 2 and 3 and so on.
Okay, got
So
it. Thank you.
we don't, yeah.
Okay.
Yeah. Okay. So yeah, so this one, the intersection is going to be 0. Was there someone else who had a question? The class is going to end soon, so I guess we'll have to end here. But your class ends at 10:10, right? If I'm correct.
Yes.
Okay. All right. So yeah, does anybody have? I guess I'll just stop for questions. Unless nobody has any questions, then I can define something else. But is this okay? Okay, so I'll just do just one definition. This definition is just in the textbook, so I included it, but we're not going to talk too much about it for now, at least. So we say that two sets are disjoint if their intersection is the empty set. So disjoint, I'll underline it. So if you have A intersected with B and that's equal to the empty set, then you say A and B are disjoint. So that's just the definition of disjoint. Yeah. So I don't know, for example, 1, 2, intersected with 3, oh wow, that 3 looks so funky. Okay, 3, 4 would be the empty set because they don't have any elements from the other set, and so they're disjoint. Okay, that's pretty simple. It's just like an addition to intersections. But if does anybody have any questions on this or anything from today or before? If not, then I'll end here because it's 10:10 now. So you're all free to leave now. And yeah, if anybody has any questions, I can stay here for a couple of minutes until you all leave. But yeah, I'll stop sharing. Okay, so class is over, so you're free to go.
Okay, thank you.
Thank you.
Yeah, no problem.
Hey, Sarah.
Oh, hi, Mark. I thought you left.
I did, but I just came back for the last minute. I put a timer
okay.
on.
All right. Hi.
How'd it go?
I think it went well. I was kind of nervous initially, so I think I was kind of rushing, but it was just review, so I hope it was okay. I hope I didn't like say anything incorrect just because I was rushing. But yeah.
I'm sure it's totally fine.
Yeah, so I think it went okay. I did try to include some harder examples, like when you have the union of closed